Hello everyone, welcome to the channel Statistical Hub. So this is a lecture on vector spaces. So for understanding this concept, first we need to know that what is vector. Okay, so vector is that quantity which has a magnitude and direction. Okay, now let's understand this by the concept of force. Let's say if I am, this is me. Okay, if I am applying the force in the right direction. This is point O and this is point B. If I'm applying the force in the right direction, then the length, which is magnitude of this, became OP. This is our length and the direction is towards P. So this is my OP vector. And if I say that if I am applying an additional force on O, which is towards Q, somewhere like this, this is point Q. Okay, this is my vector OQ. Okay, then the resultant of these forces, which is sum of these forces, is Q plus P, which is here Q plus P. So this is what the resultant of these two forces became parallelogram. Sorry, my drawing is not that good. Parallelogram. So this is our parallelogram OQRP. Now, if I multiply the force towards the P direction, it became the new vector OP became OW. If I multiply the force, which is OW equals to twice of OP. Okay, I am actually doubling the force. And when I double the force, then the new vector OW became OP. So from here, we got the concept of vector addition and scalar multiplication. Okay. So what is a vector? Vector is an ordered set of elements of a field. Okay. Represented as, let's say this is our U vector which has corresponding elements A, B and C. Now let's understand vector addition and scalar multiplication separately. So let's say I have two vectors, vector U and another vector which is our vector B, which has elements A dash, B dash and C dash. Then the sum of these two vectors U plus V became A plus A dash, B plus B dash, C plus C dash. And there is some scalar K and I multiply this scalar with the vector U, then it became KA, KB and KC. Let's see it geometrically, which is X, Y. This is my vector U. Okay. Let's say this is my vector U and this is my vector E. Now what we have studied here is that the sum of these two vectors became parallelogram. Okay, which is U plus V, then the sum of these two vectors is like this. There the U plus V vector became the components of A dash plus A dash, B plus B dash and C plus C dash. This is vector addition. Okay. Now let's see of scalar multiplication. This is our vector U, and if I multiply this U vector by any scalar K, then the new vector became KU. Okay. So this is in the same direction. We are applying the force in the same direction towards U, then it became KU. Okay, so this is scalar multiplication. Now we have some special vectors like which we use normally, which is null vector. Null vector is that vector which has all of its elements as 0, represented as 0 equals to 0, 0, 0. Okay, and there is one which is unit vector. unit vector represented as E1, where the first element is 1 and others are 0. E2, where the second element is 1 and others are 0. Towards En, which is only nth element is 0, nth element is 1 and others are 0. This is our unit vector, and there is one more which is important to study, which is sum vector. Sum vector. What is sum vector? Sum vector is as like this, which is 1 and where all the elements of this vector are 1, represented as 1x equals to sigma I going from 1 to n xi, where x is any vector. Okay, so let's first understand what is n space. N space, what is n space? The set of all n tuples of real numbers. The set of all n tuples of real numbers r's power n is n space. Okay, and there is one more thing which you must have heard, which is Euclidean n space. And what is that? Represented as e's power n. What is Euclidean n space? So the space e's power n with the operations of vector addition, scalar multiplication, and dot product is called Euclidean n space. Okay, so we'll study product. First, we'll know that what is the dot product. Okay, so what is the Euclidean n space? It has to satisfy three properties. That if I say that a comma b, the elements which belong to e's power n, then the addition of these must belongs to e's power n, which is vector addition. And second one, that if a belongs to e's power n, there is lambda, which is a scalar, then the multiplication of this a with the scalar must also belongs to e's power n. And the third point is that there is a non-negative quantity. There is a non-negative quantity associated with, let's write it. There is a non-negative quantity associated with any two vectors a and b called distance between a and b. So in the third point we are talking about dot product, basically dot product. Okay, so now let's understand what is the dot product. Dot product, or you can also say inner product. So basically the dot product tells us how much of the vector u, let's say vector u, is pointing in the same direction to another vector. Let's say name it as v. Okay, so it tells us that how much of the vector u is pointing in the same direction as v. Okay, so now let's consider we have two vectors. We are considering two vectors, vector u and vector v. Okay, with the elements a1, b1, a1, a2 to an, and vector v with b1, b2 to bn. Then the dot product of u dot v equals to a1 b1 plus a2 b2 to an bn. Now the dot product u dot v is greater than equals to 0. Okay, and if u dot u equals to 0, if I'm dot producting the u with the u, if this equals to 0, that means that u is equals to 0. Okay, now from this we got some properties like this, that if u dot v equals to 0, then the vector u or v are perpendicular to each other. What? These vectors are orthogonal, or we can say these are perpendicular to each other. And if the dot product u dot v is greater than 0, then they vector u and v are in the similar direction. And if their dot is less than 0, that means if their dot is negative, then they are moving in opposite direction. Okay. Now from this we have to understand the concept of length. What is the length of a vector? Length, or you can also say the norm or length of a vector. Norm or length of a vector, we are checking here the distance between any vector from the origin. Okay, when we are checking the length, we are checking the distance from origin to, let's say, vector u. Okay, so norm of a vector u is non-negative square root of u dot u. I have vector u with a1, a2 to an. Then the norm of a vector or length of a vector is non-negative square root of u dot u, and it is represented as u. This is the length. Now length of u equals to root of a1 square plus a2 square to an square, which is u dot u. Okay, so from this we can say that u is equals to 0 if u equals to 0, that the length of the vector is 0 if the vector is became 0. Okay, now there is an important concept which is unit vector, that how can we convert any vector to a unit vector. Okay, what does it mean that a vector is a unit vector? Any vector, let's say u, is called unit vector if the norm of u is 1. The norm of u is 1, or you can say that u dot u equals to 1, that the length of the vector, if the length of the vector is 1, then we say that it is a unit vector. Now there are many vectors which has whose lengths are not 1, so we can normalize them, or we can make them unit vector like this. Let's say I have a vector v, and this is normalizing. The conversion of any vector to a unit vector is called normalizing v. Okay, I am normalizing v by dividing the vector v to its magnitude, or you can say length, by dividing it by length. So this is our unit vector. Actually, unique unit vector in the same direction as v. Okay, so we can convert any vector to the unit vector by dividing it from its length. Okay, now let's take another page. Let's understand the concept of distance. What is the distance between two vectors? How can we calculate the distance between two vectors? So we generally calculate the distance between 2 points. How do we calculate the distance between 2 points? If I want to find the distance between these 2 points A and B, then what I do? I just subtract them. B minus A is my distance. Okay. Similarly goes for the vectors. If I want to know the distance between vector U and V, the corresponding elements of A1, A2 to An, as we are taking earlier, and V with the elements of V1, V2 to Vn, then the distance between these two vectors, let's say D, U, comma V, became, we have to find the length of U minus 1. Okay, so we'll represent it like this. It became A1 minus B1 whole square plus A2 minus A2 whole square to An minus An whole square. This is the distance between the vector u and v. Let's write it. That u is my a1 to an. Okay, and v is vector v1, v2 to vn. Then this is the distance. This is the distance between u and v. which is Schwarz inequality. It says that for any vector u and v in R's power n, we have dot product of u dot v is less than equals to their corresponding lengths. Length of u into length of v. This is our Schwarz inequality. We are going to use that. See there. Okay. And there is one more inequality which you must have studied, which is Minkowski or triangle inequality. Triangle inequality. So for any vector u comma v, the triangle inequality becomes that the norm of u plus v is less than equals to norm of u plus norm of v. Okay, these are actually coming from the length. Here in Schwarz inequality and Minkowski inequality, these inequalities are formed by the help of length. Actually, we are calculating the length here. Okay, and when I'm talking about triangle inequality, for any three vectors u, v, w, the triangle inequality became that u minus v plus v minus w is greater than equals to w minus v. Okay, this is our Schwarz inequality and triangle inequality for the two vectors and for three vectors. Now let's understand the concept. What is the angle between two vectors? Angle between two non-zero vector u, non-zero vector u comma v in R's power n. So when we talk about the angle, okay, how do we do this? So let's say this is my vector u and this is my vector v, and this is the angle made by these vectors, which is theta. Okay, now I want to find out that angle, that what is the angle made by these vectors. So how do we do this? This angle is for finding this angle, we'll do cos theta equals to u dot v upon norm of u, norm of v. We'll see it later that how we find this cos theta. Okay, which is equals to, now first we'll see that what is the range of cos theta. Cos theta lies between -1 to 1. So our cos theta value -1 to 1 cos theta. -1 to 1. So -1 to u dot v upon norm of u into norm of v. Okay, so why are we applying cos theta here only? We are using cos theta here only because it is satisfying our both properties, which is, if you from this look about Schwarz inequality, what is our Schwarz? Schwarz is that u dot v is less than equals to mod of u dot v is less than equals to norm of u and norm of v. 1 minute, have I applied? Okay. Norm of u and norm of v. Okay, this is satisfying Schwarz inequality, and it is also satisfying the definition of orthogonality, which we have studied in the dot product orthogonality. How? See this, if u dot v equals to 0, that means that theta equals to 90, which is, that theta becomes 90, it means that u and v are perpendicular to each other. So it is satisfying both the properties of Schwarz and orthogonality. Okay, now let's see that I have vector u and v. This is my vector u, this is my vector v, and this is my vector u. Okay, I want to see the perpendicular projection of u onto v. Perpendicular projection, which is like this, onto v. This is perpendicular projection of u onto v. Okay, and this angle u and the vectors u and v are making angle theta. Okay, now the perpendicular projection of u onto v is vector u star. This is vector u star. Okay, and it has magnitude of u star 2. Okay. Now I want to find that vector u star that is perpendicularly projected to the vector p. Now how can we do this? If firstly I want to find the magnitude of the vector, that is length of the vector u star, the new vector which is this is our point C, let's say. Okay. Now firstly I want to find the magnitude of this vector, that is length of the vector u star, which is equals to, if I apply here cos theta, which is equals to base upon hypotenuse, then cos theta equals to became, what is our base? Our base is u star and our hypotenuse is u. Okay, so my u star, the length of the u star became u cos theta. Okay, u cos theta. And what is the formula for cos theta? The formula for cos theta is u dot v upon norm of u and norm of v. This will cut, and the magnitude of the new vector u star became u dot v upon norm of v. Now I want to know the vector u star. I want to know the vector u star. This is the magnitude of the u star. I want to know the vector u star. Okay, so as you can see that the u star is moving towards the direction of v vector. Okay, so for obtaining the vector u star, what we do? We'll apply unit vector concept here. Okay, if we'll multiply the unit vector of v, which is of length 1, to the magnitude of u star, we'll get a vector u star. So we'll for getting the vector u star, we'll multiply the magnitude length of u star by the unit vector, which is going towards. Why are we multiplying the unit vector? Because the u vector, u star vector, and the v vector are going in the same direction. So we are multiplying the unit vector here, which became v upon magnitude of v, length of v. So if we'll open it, so what is the magnitude of u star, which is u dot v upon norm of v into v upon v. Okay, so this is equals to u dot v upon length of v whole square into v, and this is the formula for projection. This is the formula for projection, that when a vector u is being projected to a vector v. Okay, this is the projection formula. Projection of u comma v equals to u dot v upon length of v's whole square into v, which can also be written as u dot v upon v dot v into v. This is the formula for projection. Okay. Now from these vector operations, there is an interpretation. We can interpret it like this, that let's say I have n values of variables x1, x2 to xn. These are the n values of variable x, of variable x. Okay, now what is the mean of these vectors? X bar is the mean of these vectors, which is 1 upon n sigma I going from 1 to n xi. Okay, I can also write it like this, 1 upon n into 1 dash x. This is my sum vector. Okay, where x is x1, x2 to xn. I have represented the mean in the form of sum vector. Okay, now if I see the deviation of these n variables from the mean, then what did this become? The deviations are x1 minus x bar, x2 minus x bar to xn minus x bar, and these deviations can be represented as x minus x bar dot 1, which is equals to x1, x2 to xn minus x bar, x bar, x bar. Okay, x1 minus x bar, x2 minus x bar. Okay, so these deviations can be represented as x minus x bar dot 1. Now We have studied the concept of measure of dispersion. In the measure of dispersion, what we do, we take the distance between x and x dot 1. That is the length of the deviations vector. Okay, we are taking the length of the deviations vector. Deviations vector. So if you find the length of these vectors, that is the length of x minus x dot 1, this is our deviation, then it became root of sigma xi minus x bar whole square. Okay, the corresponding squares of this. This is our length. Then if I have a set of ordered pairs, if I have a set of ordered pair like this x1 y1 to xn yn, I have n pairs of values of x and y. These are my two vectors x and y. Then the deviations for this is defined as, for x I have the deviation, for x vector I have the deviation x minus x bar dot 1. This is my deviation d1. And for y vector similarly goes for y minus y bar dot 1. Okay, which is my deviation d2. Let's see it like this. This is my vector y and this is my another vector x. Okay, and the deviation of these vectors, which is x minus x1 and y minus y1, this is my y minus y1, which is can be written as y dot 1 bar. Okay, this is the difference, and this is y dot x dot 1 bar, x bar dot 1. Okay, this is x bar dot 1, and this is the difference between these two vectors d1 and d2. These are the deviations d1, d2, x bar minus x1 bar and y bar minus y vector minus y bar bar. Okay, now if theta is the angle between these two deviations d1 and d2, if theta is the angle, then if the angle is 0, if the theta is 0, if theta equals to 0, then what does this mean? That x and y are on the same line. It means that x and y are on same line. And if the angle is smaller, the smaller the angle gets, the smaller the angle, that means closer the vectors goes closer to the line, closer to a line. Okay, so there is a linear relationship between this. If the angle is going smaller, then the vectors are coming closer to the line. So there is a linear relationship between these. So we'll define cos theta. We'll define cos theta from here like so for defining the cos theta, first we'll do what here? We'll do the perpendicular projection of here. We'll get the help of take the help of perpendicular projection. If I project this vector d1 to vector d2 like this, if I perpendicularly project this, then I want to find the perpendicular projection, that is the magnitude. Okay, then how do we find this? I'll get d1 and vector. Let's say this is my vector u first. Okay, vector u, which is equals to d1 cos theta, d1 cos theta. Okay, and why am I multiplying this here? Because I am using u vector here, because I have taken this u vector as a unit vector of y, unit vector of d2 actually, unit vector of deviation d2. So if I am applying a u vector is basically my unit vector, which is d2 upon d2. So by putting the unit vector here, I got d2 upon d2, which is equals to d1 cos theta. So I got d1 dot d2 equals to d1 d2 cos theta. Okay, now my cos theta became cos theta equals to d1 dot d2 upon d1 d2. This is how we got the our angle cos theta. Okay. Now, how do we get this? d1 norm of u and d2 cos theta. It is similarly as we have done in the projection. We have done in the projection that we have to find the magnitude. We have to first, what we do, we have first find the magnitude, and for finding the magnitude we have applied the angle theta. And when we apply the angle theta, that what is cos theta? Cos theta is based upon hypotenuse, and by applying based upon hypotenuse concept, first we need to know that this vector d1, vector d1, we are using the dot product here, that d1 dot u vector equals to d1 cos theta, which is based upon hypotenuse. Based upon hypotenuse, this is the magnitude. What? This is the magnitude of this u vector, this part. Okay, this can also be written as, let's say, the magnitude of u is u, which is equals to d1 cos theta. Okay, so we are taking here the magnitude, which and this the magnitude is represented as the dot product like this d1 dot u. Okay, so what we are doing here is we are taking the dot product here. We are taking the dot product here. See it like this, that we have cos theta equals to based upon hypotenuse. Okay, what is the magnitude of the base? We have the magnitude. We are taking the magnitude of the base as u, and we are taking the magnitude of hypotenuse as d1, which is d1. Now I don't know the magnitude of u, and I have to find that magnitude, and we'll find that magnitude by perpendicularly projecting that, which is by the help of dot product. By the help of dot product. And how can we do this? Dot product is the one which gives us that how much a vector u, any vector, let's say how much the vector x is pointing in the same direction as vector y. So what we do here is we are doing d1 dot u. This is my vector u. Okay, so this will give us the magnitude of u, and we'll get cos theta equals to, sorry, d1 dot magnitude of u equals to d1 cos theta. Now you can, if you can identify this, that cos theta equals to d1 into d2 upon norm of d1 into norm of d2. And what are our deviations d1 and d2? They can be represented as, not represented, they have we have taken them as x bar dot 1 y minus y bar dot 1 upon, similarly here, x minus x bar dot 1 and y minus y bar dot 1. And these deviations are sigma xi minus x bar and yi minus y bar upon root sigma xi minus x bar whole square and root sigma yi minus y bar whole square. Can you recognize this formula? This is the formula of correlation coefficient Rx1, which is correlation coefficient between x and y. So from the angle between u and v, from the projection concept, we have got that the formula for correlation coefficient must have come from this. Okay, and what is the range of correlation coefficient, which is 1 minus 1 to 1, and if Rxy, which is correlation coefficient, equals to 0, that means the angle between them is 90 degree. If Rxy equals to 1, that means the angle is 0, and if it is minus 1, then it means that the angle is 180 degree. Okay, this is all about the concept of angle and projection. Okay, now let's see our main concept, which is vector spaces. Vector spaces. Okay, so for this, let V be a non-empty set. Non-empty set with two operations. With two operations. First, vector addition. Vector addition, which is if u comma v belongs to v, then u plus v also belongs to v. And second one is scalar multiplication. Scalar multiplication. that if u vector belongs to the V, then there is a scalar which belongs to K. Here it defines the field of scalars. What? It is the field of scalars. Then KU also belongs to V. So there are certain axioms for defining the vector space. We'll study them. That V is called vector space. V is called vector space over field K. We are taking K here. Why are we taking K here? Because we are taking the vector spaces over the general field. Okay, over the general field which is K. If following axioms are satisfied, these are certain axioms for any set to be a vector space. Okay, let's say first axiom, which is I have the vectors u, v, w, which belongs to V. Then these certain axioms have to be satisfied for V to be a vector space. If u, v, w belongs to V, then u plus V plus W equals to u plus V plus W, which is the property of associativity. Okay. And the second one is the existence of neutral element, which is 0 belongs to V, such that 0 plus V equals to V plus 0 equals to V. This is the existence of neutral element. Okay. Now the third one is that for each u belongs to V, there is a vector. There is a vector in V by minus u. Like u plus minus u equals to minus u plus u equals to 0, which is the existence of negatives. Okay. And the fourth property is of commutativity, that if u plus v equals to v plus u, this is commutativity. Okay. So let's understand the first fifth one. Then we'll talk later about it. Fifth one is distributive of scalar multiplication over addition in V. Let's say I have two vectors which I am adding u plus v, and I am distributing this field k over there, which is ku plus kv, where k belongs to the field of scalars. This is called distribution of scalar multiplication over addition in V. Okay. And the second one is a plus bu, which is equals to au plus bu. For each a comma b belongs to k, a comma b belongs to k. This is the distribution of scalar multiplication over field. Over field. And the seventh one is that of associativity, that ABU equals to ABU, for A comma B belongs to K. This is of associativity. And 1U equals to U, where 1 belongs to K. This is the property of unity. So these are the certain axioms that has to be satisfied for a set to be a vector space. A vector space is a linear structure. What a vector space is a linear structure, and is also called linear space. Linear space. Now there is one thing, that vector v with the operation of addition is commutative group under addition. That v is commutative under addition. What does this mean? It means that any sum of vectors, any sum v1 plus v2 to vm of vectors does not depend on order. Order, it does not depend on order. And the second thing for this is that zero vector is unique vector and there exists a negative vector of a vector, which is if a vector u, then there is exist a negative of u, and which is unique, and zero vector which is also unique. Okay, now say this, that the v under addition, that is that addition is a map, addition is a map from v cross v to v. Okay, v cross v to v, and it is said to be the internal composition. Internal composition, that we, if we are talking about the vector addition only, that which is mapping from v cross v to v, then it is said to be the internal composition. And if I am talking about the dot, which is multiplication, okay, that is v over the field of scalars v k dot, and dot is a map from k cross v to v, and this is called external composition. Okay, now there is an important theorem. There is an important theorem. Let V be a vector space over K. Okay, let V be a vector space over K. The first thing is that if the K is belongs to K, field of scalars, and 0 is belonging to vector space V, then K0 equals to 0. Okay, and if 0 is belonging to the field of scalars and vu is belonging to v, then also u0 equals to 0. But there is a difference, that here the scalar, here the vector is 0 and here the scalar is 0. Okay, and the third point is, if ku equals to 0, where k is belonging to the field of scalars and u is a vector, then in this case either k equals to 0 or u equals to 0. Okay, and the fourth one is minus k of u equals to k of minus u, which is equals to minus k. These are the basic properties. Basic. These are just some basic concepts, but here we are just trying to say that here the vector is 0 and here the scalar is 0. So there is an important point to notice, that if the vector is 0 and if the scalars are 0. Okay, now as I am saying earlier, that a vector we are talking here is over the field K. Over the field K. We are taking this field K as a general field. As a general field. Okay. We are not defining it real, complex, or anything. We are just taking it as a general field, because as you can see that if I am taking this as a finite field, the finite field is more important in the study of computer science and coding theory, actually coding theory, design of experiments. And if I take the vector space over the field of rational numbers, then they are more important of like number theory, design of experiments. Okay, and if I talk about the vector space over let's say complex field, then they are more of use in eigenvalues. Okay, so we are not taking a particular field here, we are talking about the general field, over the general field. Now there is a note, there is a point which is very important, that every field is a vector space over itself. What? Every field is a vector space over itself. They say it like this, that natural number is a subset of integers. Integers are subsets of rationals, and rationals are subsets of reals, and reals are subsets of complex. Okay. Now we can see that complex over complex form a vector space. Okay. Real over real form a vector space. Rational over rational form a vector space. But integer over integer doesn't form a vector space, because for forming a vector space it has to be a field first, but integer to integer is not a field, because it doesn't satisfy the property ith. which I have taken earlier, which is x dot x inverse equals to 1, the existence of inverse. Okay, and 1 by x is not an integer. That's why it doesn't satisfy this property. So z, the set of integers, is not a field and neither a vector space. Okay, there is one thing also, that every field is a vector space over its subfield. What is that? Every field is a vector space over its subfield. Okay, so this is about the fields and the vectors. Now let's see some examples of this. If I'm talking about the space k is power n, okay, so I'm taking this k as any arbitrary field, then k ki power n here denotes the set of all n tuples of elements in k. What? Set of all n tuples of elements in k. Then here k ki power n is a vector space over k. K ki power n is vector space over k by first vector addition as a1 a1 a2 to an plus b1 b2 to bn, which became a1 plus b1 a2 plus b2 to an plus bn. And scalar multiplication, which is k of a1 to an is equals to k of a1, k of a2 to k of an. And third one is the existence of zero element, which is 0 0 0 0 0 0 vector. Okay, and the fourth one is to existence of negative vector. That if I negatify this vector, minus of a1 a2 to an became minus a1 minus a2 to minus an. So this field of scalars, this is an arbitrary field k ki power n, vector space over k is a vector space. So the space k ki power n is a vector space. This forms a vector space. Okay. Now if I talk about the polynomial space, what? Polynomial space, which is p of t. Okay. So p of t denotes the set of all polynomials of the form pt equals to a naught plus a1t plus a2t square plus as t bar s, where s equals to 0 1 2 2 and s. N equals to p of t. This is our polynomial set where a, I, r belongs to k. Then this p of t is a vector space over k. What? P of t is a vector space over k by vector addition and scalar multiplication and zero polynomial. How? Let's see it like this. I can represent this pt like sigma n equals to 0 to s, 0 to s ai t is the power I equals to 0 to s and ai t is power I, and another polynomial which is qt equals to sigma I equals to 0 to s bi t is power I. Then the addition of these two polynomial pt plus qt equals to sigma I equals to 0 to s ai plus bi t is power I. And the scalar multiplication, let's say if I'm multiplying lambda with the polynomial pt, then it became lambda sigma I equals to 0 to s ai t is power I. Then this is the scalar multiplication. And the existence of zero polynomial, the existence of zero polynomial is when the corresponding ai's became 0. Okay, then we'll say that there is a zero polynomial. So it is forming a vector space. The polynomial space PT is forming a vector space over vector addition, scalar multiplication, and zero polynomial. Zero polynomial. Now let's talk about an important space which is matrix space. Matrix space. Let's say M of M over N. This also forms a vector space with the usual operations. Let's say I have a function f of x which denotes the set of all functions of x. Okay, functions of x. Now we are talking about the function space. Function space fx. Function space fx. The matrix space m of n comma n. It is a vector space. It is a vector space with the vector addition, scalar multiplication. As you can see that matrices can be added and multiplied with a scalar easily. And there is a zero matrix also. So it also forms a vector space. And there is a one important thing which is a functional space. Functional space is f of x. Functional space is f of x, and if I add the functions, let's say I have a function f of x and g of x, then addition of these functions f plus g of x equals to f of x plus g of x, and the multiply of the function fx by the scalar k became k of fx equals to k f x, where k belongs to a field k. The existence of 0x equals to 0, existence of negative minus of fx equals to minus fx. So from this we can say that the space k ki power n, it forms a vector space. Okay, polynomial space pt, it is also forming a vector space. Matrix space, it is also vector space. And the function space, it is also forming the vector space. Okay, so these are the main vector spaces which we'll use in our further studies. Okay, okay, so this is all about vector spaces. Thank you.